Somewhere in the dark, there is a galaxy the size of our own, and it is almost entirely empty of light. Welcome to the Sleepy Lab. Tonight, we drift toward a place called Dragonfly 44, a galaxy that should be filled with hundreds of billions of stars, and yet holds barely a billion. A structure so faint it hid from us for decades, invisible not because it isn't there, but because almost nothing inside it shines. If this kind of quiet wonder helps you sleep, consider subscribing, one sleepy soul at a time. Now, let's begin. In 2016, a small team of astronomers made an unlikely discovery using an unlikely instrument. Not a great observatory on a mountaintop, not a space telescope costing billions of dollars. What they used were camera lenses, the kind sold in photography shops, the kind a portrait photographer might carry in a bag. The instrument is called the Dragonfly Telephoto Array, and it was assembled, in part, from off-the-shelf telephoto lenses, 11 of them. Working in parallel, their light pooled together into a single, extraordinarily sensitive eye. The array takes its name from the dragonfly, an insect whose compound eye uses many small lenses to build one wide, detailed image of the world. It is a humble design for a profound purpose. Most large telescopes are built to find things that are bright and compact, a sharp point of light against the dark. The Dragonfly array was built for the opposite. It was designed to find things that are vast and almost invisible. Its lenses are coated to suppress scattered light and internal reflections, the kind of optical noise that drowns out faint, diffuse glows in conventional instruments. And so, it was this quiet, patient instrument, not a giant mirror, not a billion-dollar satellite, that first revealed Dragonfly 44 to human eyes. The galaxy sits within a region of sky called the Coma Cluster. The Coma Cluster is a dense gathering of galaxies, over 1,000 of them, bound together by gravity, drifting as a single enormous structure through the universe. It lies roughly 320 million light-years from Earth. To hold that distance gently in mind, light, which crosses the entire Earth in less than 1/10 of a second, would need 320 million years to reach the Coma Cluster from here. The light we observe from that region tonight left its source before complex animal life had fully taken hold on this planet. Within that cluster, among those 1,000 galaxies, Dragonfly 44 had been hiding in plain sight. In size, it is not small. The galaxy spans roughly 60,000 light-years from edge to edge, comparable in diameter to our own Milky Way. If you were to place the two side by side, they would appear, at first glance, to be roughly the same scale, two broad, roughly circular structures, each tens of thousands of light-years wide. But there the resemblance ends. The Milky Way contains somewhere between 200 and 400 billion stars, vast rivers of them, wound into spiral arms, glowing with the accumulated light of countless suns burning across billions of years. Dragonfly 44 contains roughly 1 billion stars. 1%. Imagine a city the size of a great metropolis, the streets laid out, the avenues stretching for miles, the infrastructure of something enormous. And then imagine that city almost entirely empty. A building here, a building there, long stretches of silence between them. That is something like Dragonfly 44. The same span of space, a fraction of the light. Because its stars are spread so thinly across such a wide area, the galaxy's surface brightness, the amount of light it emits per patch of sky, is extraordinarily low. Lower than most telescopes were designed to detect. Previous sky surveys, optimized to find compact, bright sources, passed over it entirely. It was not that they looked and found nothing. It was that the instruments were not built to see what Dragonfly 44 was offering. A whisper in a room designed to hear only shouts. And so for decades, it went unrecorded, unnamed, unknown. A galaxy the size of our own, drifting 320 million light-years away, holding its billion quiet stars and waiting, without knowing it was waiting, for an instrument patient enough to notice. The Dragonfly array noticed, and what it found, when astronomers looked more closely, was stranger than the galaxy's faintness alone. Because Dragonfly 44 is not simply a sparse galaxy. It is not merely a place where star formation happens slowly, or where stars are spread unusually wide. It is something more unsettling than that. The stars it does contain, those billion quiet suns, are moving. And the way they are moving does not make sense if stars and gas are all there is. But that is a question for a little later in the night. For now, let the image settle. A galaxy the size of the Milky Way, holding 1% of its stars, invisible to most of the instruments we built to study the sky, discovered not by the largest telescope in the world, but by 11 camera lenses working quietly together. There is something in that worth sitting with. The universe does not always announce its strangest places loudly. Sometimes the most extraordinary things are the ones that barely glow, the ones that ask, gently, for an instrument willing to look slowly and softly and long. Dragonfly 44 was always there. We simply had not yet learned how to see it. There is a name for what Dragonfly 44 is. Astronomers call it an ultra-diffuse galaxy. It is a quiet, technical phrase. But what it describes is something that took a long time to even recognize as a category, because for most of the history of modern astronomy, objects like Dragonfly 44 were simply not seen. Not because they were rare, not because they were distant, but because the tools we built were not designed to find them. Sky surveys are built around assumptions, and for decades, the assumption was that galaxies are bright, compact, concentrated. A survey sweeping the sky looks for peaks of light, places where photons arrive in numbers large enough to register clearly against the background. Dragonfly 44 does not do that. Its light is spread so thinly across so much space that no single patch of it is bright enough to trigger the detection thresholds those surveys were built around. It was not hidden, it was simply below the threshold of what we thought to look for. The formal definition of an ultra-diffuse galaxy is precise in the way that scientific definitions tend to be. An effective radius larger than 1.5 kiloparsecs. A surface brightness fainter than 24 magnitudes per square arcsecond. Those numbers may not mean much on their own, but held together, they describe something specific. A structure that is genuinely large. Not a dwarf galaxy, not a small smudge, but spread so wide and glowing so faintly that it falls beneath the notice of instruments built for brighter things. The category barely existed before the 2010s. Not because ultra-diffuse galaxies did not exist, they did, as they always had, drifting through clusters and voids across the observable universe. But because no one had yet built the right kind of eye to find them in any number. The Dragonfly array changed that, and once astronomers knew what to look for, they began finding ultra-diffuse galaxies in surprising abundance. The Coma cluster alone, the same dense collection of galaxies where Dragonfly 44 lives, turned out to contain hundreds of them. But Dragonfly 44 stood apart, even among its own kind. Its total stellar mass, the combined weight of every star it contains, is estimated at roughly 1 billion solar masses. 1 billion suns, each quietly burning, spread across 60,000 light-years of space. That sounds like a large number, and in some contexts, it is. But set it beside the Milky Way, which contains something closer to 1 trillion solar masses in stars, and the difference becomes clear. Dragonfly 44 holds about 1% of what our own galaxy holds. 1% of the stars, spread across a comparable volume of space. A vast, dim, nearly empty place. And yet, the stars that are there are moving. This is where the story shifts, because the motion of those stars is not what it should be if stars and gas were all the galaxy contained. When astronomers measure a galaxy's mass, one of the most reliable methods is to watch how its stars move. Stars in a galaxy are not still. They orbit, they drift, they trace paths through the gravitational field that holds them. and the speed of those paths encodes information. A star moving quickly is being pulled by something strong. A star moving slowly is held by something weaker. The measurement used for a galaxy like Dragonfly 44, one too distant and too faint to map individual stellar orbits, is called velocity dispersion. It is, in essence, a measure of how spread out the speeds are, how much variation exists in the velocities of the stars as a group. A high velocity dispersion means the stars are moving fast relative to one another, and fast motion in a gravitationally bound system means there is a great deal of mass doing the binding. The velocity dispersion of Dragonfly 44's stars is approximately 47 kilometers per second. 47 kilometers every second. That is not a gentle drift. That is stars moving with real urgency through a galaxy that, by all appearances, should not be able to hold them. When astronomers calculated how much mass would be needed to keep those stars from simply flying apart, to maintain the galaxy as a coherent structure rather than a scattering of suns dissolving into the void, the number they arrived at was far larger than 1 billion solar masses. Far larger. The stars alone, by a wide margin, are not enough. The gas alone is not enough. Everything visible, everything that emits or reflects any form of light, is not enough, not even close, to account for the gravitational grip that is clearly, measurably, holding Dragonfly 44 together. Something else is there. Something with mass. Something exerting gravity. Something that is doing the quiet, patient work of keeping this galaxy intact across billions of years. And yet, it gives off no light. It reflects nothing. It absorbs nothing. It leaves no trace in any wavelength that any telescope of any kind has ever been built to detect. This is the thing that makes Dragonfly 44 more than a curiosity about star formation or an interesting edge case in galaxy classification. It is a window, one of the clearest windows we have found, into something that makes up the vast majority of all the mass in the universe, and that remains, despite decades of searching, almost entirely unknown: dark matter. The name is simple. The reality is stranger. It is not dark in the way that a shadow is dark, or the way that deep space between stars is dark. It is dark in a more fundamental sense. Dark because it has no relationship with light at all. It does not shine. It does not block. It does not scatter photons or absorb them or bend them in any way that leaves a direct imprint on a detector. It simply is massive and present and invisible. The stars of Dragonfly 44 move the way they do because they are embedded in something enormous, a halo of this unseen material, far larger and far more massive than the galaxy's visible parts. The stars are, in a sense, incidental, passengers. A thin, luminous skin stretched over a structure made almost entirely of something we cannot see. And this is not a small discrepancy, not a rounding error in the accounting of the universe. The total mass of Dragonfly 44 is estimated at roughly 1 trillion solar masses. The stars account for about 1 billion of those. 1 billion out of 1 trillion, 1 part in 1,000. The rest, 99.9% of everything that makes Dragonfly 44 what it is dark matter. There is a particular kind of stillness that comes with sitting inside a fact like that. Not the stillness of emptiness, but the stillness of something very large, very old, and very patient, waiting to be understood. Dragonfly 44 is not simply a galaxy with few stars. It is a dark matter halo that happens to contain a small number of stars, almost as an afterthought. A structure defined not by what it shows, but by what it hides. In the stars, those billion quiet suns moving faster than they should are the only reason we know it is there at all. But there is another way to weigh a galaxy, one that does not rely on the speed of its stars or the brightness of its light, one that looks instead at something older and quieter and stranger, scattered through the outer reaches of Dragonfly 44, orbiting slowly in the dark, are roughly 90 globular clusters. A globular cluster is a tight, ancient sphere of stars, sometimes tens of thousands of them, sometimes hundreds of thousands, bound together by their own gravity, moving as one through the halo of a larger galaxy. They are among the oldest structures in the universe. Some of them formed when the cosmos was still very young, when the first large concentrations of matter were just beginning to pull themselves together. They are not rare. Most galaxies of any significant size carry them, and over decades of careful observation, astronomers noticed something. The number of globular clusters a galaxy hosts tends to track its total mass, not its stellar mass, not the mass of its visible stars, but its total mass, including whatever dark matter surrounds it. The relationship is not perfect. There is scatter, as there always is in nature. But across many different galaxy types, across spirals and ellipticals, and dwarfs and giants, the ratio holds with a quiet consistency that is difficult to dismiss. More total mass, more globular clusters. It is as though the globular clusters are counting something the stars cannot, as though they formed in response to the full gravitational depth of the halo, not merely the luminous portion of it. The precise reason for this relationship is still a matter of ongoing study. It may be that globular clusters form preferentially in the densest early pockets of dark matter. It may be that they survive longer in more massive halos, where tidal disruption is less severe. The details remain open, but the pattern itself, the rough proportionality between cluster count and total mass, has proven reliable enough that astronomers now use it as an independent tool, a way of estimating a galaxy's true mass simply by counting the ancient spheres of stars drifting through its outer dark. And so, when astronomers turned that method toward Dragonfly 44, they found something that quietly confirmed what the stellar velocities had already suggested: 90 globular clusters. For a galaxy with only 1 billion solar masses and stars, that number is far too high. A galaxy that small, that dim, that sparse, by the logic of its visible content alone, should carry only a handful, perhaps a dozen, perhaps fewer. But 90 is not the number of a small galaxy. 90 is the number of something much larger. The Milky Way, for comparison, holds somewhere between 150 and 200 globular clusters. Our galaxy contains hundreds of billions of stars. It is, by any ordinary measure, a vast and well-populated place, a spiral of light 100,000 light-years across, with a dense, bright core and long, curving arms trailing through space. And Dragonfly 44, with its billion quiet suns and its nearly invisible face, carries almost as many globular clusters as that. Not quite as many, but close enough that the comparison settles into the mind with a particular weight. A galaxy 1% the size, in terms of stars, carrying perhaps 60% as many of these ancient orbiting spheres. The globular clusters do not know about the stars. They orbit the halo. They respond to the full depth of the gravitational well beneath them. And that well, in Dragonfly 44, is enormous, far deeper than the thin scatter of visible stars would ever suggest. This is what makes the globular cluster count so valuable. It is independent. It does not rely on measuring how fast the stars move, or on modeling the dynamics of a system we can barely resolve. It simply asks, how many of these ancient objects are out there, tracing the edges of the dark? And the answer, in this case, is the same answer the stellar velocities gave. The same answer, arrived at by a completely different path. In science, that kind of convergence carries a particular quiet authority. When two separate methods, using different data, different assumptions, different instruments, arrive at the same conclusion, the conclusion becomes harder to set aside. Dragonfly 44 is massive, not in the way we usually mean when we call something massive, not dense, not bright, not visibly imposing. Massive in the way a deep ocean is massive. Most of it is beneath the surface. Most of it cannot be seen. The globular clusters are like buoys, floating at the edges of something vast and dark, marking the boundary of a structure that light cannot touch. Roughly 90 of them, drifting slowly through the outer halo. Each one a tight ancient sphere, perhaps 100 light-years across, containing stars that formed when the universe was young. Stars that have been orbiting together for billions of years. long before the Earth existed, long before the sun ignited. They have been out there, in the dark around Dragonfly 44, for most of the history of the cosmos. And in a way, they have been keeping a record. Not a record written in language or in light, but in their number and in their orbits and in the quiet gravitational logic of where they are and how they move. A record that says, there is more here than you can see. There has always been more here than you can see. The stellar velocities said it first. The globular clusters confirmed it. And together, they point toward the same dark conclusion. The Dragonfly 44 is, in some deep structural sense, a galaxy defined by absence, by the vast preponderance of something invisible, by a halo of dark matter so dominant that the stars and the clusters and all the visible architecture of the galaxy are, in the end, a kind of annotation, a footnote written in light, at the edge of something that needs no light at all. There is a stillness in that thought, if you let it settle. Not a troubling stillness, more like the stillness of standing at the edge of a very deep lake at night, knowing the water goes down far beyond what you can see, and feeling not afraid of that depth, but quietly held by it. The universe is mostly things we cannot see. Dragonfly 44 is simply a place where that truth becomes unusually clear, where the invisible has not been diluted by an abundance of stars, or hidden behind the brightness of a galactic core, where the dark matter has been left, in some sense, exposed, not to our eyes, but to our instruments and to the patient logic of the numbers they return. 90 globular clusters orbiting in the dark, each one a small, ancient world of its own, each one a quiet witness to the mass beneath it. And the mass beneath them, that trillion solar masses of something we have never directly seen, never touched, never named with any certainty, holds them gently in place, as it has for billions of years, as it will for billions more. Patient, invisible, and very, very large. So those 90 globular clusters were not merely a curiosity, they were a second voice, saying the same thing the stellar velocities had already said. Two entirely different methods of measurement. One, watching how fast the stars move, one counting the ancient clusters orbiting in the halo, and both of them arriving at the same quiet conclusion. A trillion solar masses, almost none of it visible. In science, that kind of agreement carries weight. When two independent lines of evidence point to the same answer, the answer becomes harder to set aside. The globular clusters were not confirming a theory so much as confirming a fact. A fact the numbers had already been trying to communicate, patiently, through every observation made of this galaxy. And the fact is this: whatever holds Dragonfly 44 together, whatever accounts for nearly all of its mass, does not shine. It does not glow. It does not absorb light and re-emit it at another wavelength. It does not scatter the light that passes through it, the way dust does, or gas does, or anything made of ordinary atoms does. It simply does not interact with light at all. Every telescope ever built, whether it gathers visible light, or radio waves, or X-rays, or infrared, or ultraviolet, every one of them works by collecting electromagnetic radiation of some kind, and dark matter produces none of it, reflects none of it, absorbs none of it. It passes through the entire electromagnetic spectrum as though the spectrum does not exist. This is not a limitation of our instruments. It is a property of the thing itself. Dark matter is not merely dim. It is not a very faint star or a cold cloud of gas that we haven't yet found the right wavelength to detect. It is something that exists entirely outside the relationship between matter and light that we have built all of our astronomy upon. And yet, it is there. The gravity is real. The effects are measurable. The mass is present. Only the light is missing, because the light was never there to begin with. This is a strange thing to sit with. We live in a universe where almost everything we know about distant objects, we know because of light. Light carries information across billions of years and billions of light years. It tells us the temperature of a star, the composition of an atmosphere, the speed at which a galaxy is moving away from us. Light is the medium through which the cosmos speaks to us, and dark matter is silent in that medium, completely, permanently. As far as we can tell, the idea that such a thing might exist is not new. In 1933, a Swiss astronomer named Fritz Zwicky was studying this very cluster, the Coma cluster, the same dense gathering of galaxies where Dragonfly 44 now sits. He was measuring the velocities of individual galaxies within the cluster, watching how fast they moved relative to one another, and the numbers did not make sense. Galaxies in a cluster are bound together by gravity, the way the planets of a solar system are bound to their star. And just as you can calculate how fast a planet should orbit based on the mass of the star it circles, you can calculate how fast a galaxy should move based on the total mass of the cluster holding it. Zwicky did that calculation. He looked at the visible mass, the stars, the galaxies, everything that could be seen, and he worked out how fast the galaxies should be moving. They were moving far faster, not slightly faster, not within the margin of measurement error. Far faster, fast enough that if the visible mass were all there was, the cluster should have flown apart long ago. The galaxies should have scattered outward into the surrounding void, unbound, free. But they had not scattered. They were still there, still moving together, still held. Something was holding them. Something with mass. Something with gravity. Something that did not show up in any observation of the cluster's light. Zwicky gave this something a name. He called it Dunkel Materie, dark matter. It is a plain name, almost understated for what it implies. Not invisible matter, not hidden matter, not missing matter, though all of those words would also apply. Just dark. The simplest possible description of something that produces no light. He published his findings. He described the discrepancy carefully, proposed the existence of unseen mass as the most straightforward explanation, and moved on to other work. And the scientific community, for the most part, moved on without him. His idea was noted, filed away, and largely set aside. It would remain that way for decades, not disproven, not refuted, simply not taken up. The tools to pursue it further were not yet available. The community's attention was elsewhere, and perhaps, too, the idea was simply too large, too strange, too unsettling to absorb. Without more evidence than one man's velocity measurements of one distant cluster. There is something quietly melancholy about that. A person looks at the numbers, sees something real, names it carefully, and then watches the world continue as though he had said nothing. Not because he was wrong, but because the world was not yet ready to hear it. Zwicky was, by many accounts, a difficult man, sharp-tongued, combative, not always easy to work with or to listen to. History has a way of complicating the stories of people who were right too early. But the Dunkel Materie was real, whatever anyone thought of the person who named it. It was there in the Coma cluster in 1933. It is there now. And Dragonfly 44, sitting quietly in that same cluster, nearly a century later, is, in a way, the fullest expression of what Zwicky glimpsed in those velocity measurements. Not just a cluster with more mass than its light suggests, but a single galaxy, an entire galaxy, in which the invisible has almost completely overwhelmed the visible, in which the dark matter has not merely supplemented the ordinary matter, but has come to constitute nearly everything. Zwicky saw the shadow of it cast across a whole cluster of galaxies. Dragonfly 44 is the shadow itself, and the shadow has a shape. It has a size. It has a mass that can be measured, indirectly, through the motion of stars and the orbits of ancient clusters. It is not nothing. It is, in fact, most of everything, at least in this particular corner of the universe, in this particular galaxy, drifting slowly through the Coma cluster, 60,000 light-years wide and almost entirely dark. The stars within it are few and old and quiet. They burn with the low, patient light of things that have been burning for a very long time and have very little left to give. They are not the point of this galaxy. They are, in some sense, incidental, a small residue of ordinary matter that managed to collapse and ignite in the early universe, surrounded on all sides by something vast and invisible that was there long before the first of them lit up, and will be there long after the last of them goes dark. Zwicky's idea waited a long time to be taken seriously. Decades passed, the mid-20th century moved through its years, and the question of missing mass sat quietly at the edges of astronomy. Noted, but not pursued. Acknowledged, but not believed. It would take a different kind of observation, made by a different kind of scientist, to bring it back into the light. In the 1970s, an astronomer named Vera Rubin, working alongside her colleague Kent Ford, turned her attention to spiral galaxies. Not to their centers, not to their brightest regions, but to their outer edges, the dim, far-flung arms where stars grow sparse and the light grows thin. She wanted to know how fast those outer stars were moving. It was, on the surface, a straightforward question. The expected answer was already known, or so most astronomers assumed. Think of the solar system for a moment. Mercury, the innermost planet, moves quickly, nearly 48 kilometers per second in its orbit around the Sun. Neptune, far out at the cold edge, moves at barely 5. The further a planet sits from the gravitational center, the more slowly it travels. This is not a coincidence. It follows directly from the way gravity works. The Sun holds most of the mass, and its pull weakens with distance. Objects far from the center feel less of it, and so they move more gently, more slowly, tracing wide and unhurried paths through the dark. A galaxy, by the same logic, should behave similarly. Most of a galaxy's visible mass, its stars, its gas, its dust, is concentrated toward the center. The bright core, the dense inner disk. Stars near the center orbit quickly, pulled hard by all that mass nearby. Stars at the outer edges, far from the bulk of the visible matter, should feel a weaker pull. They should orbit more slowly. The rotation curve, a graph of orbital speed against distance from the center, should rise toward the middle and then fall away, gently toward the edges. That is what physics predicted. That is not what Vera Rubin found. What she found, galaxy after galaxy, was a curve that rose and then simply stayed. The outer stars were not slowing down. They were moving just as fast as the inner ones, sometimes faster than the visible mass alone could possibly explain. The rotation curve was flat where it should have been falling, and it stayed flat, out to the very limits of what her instruments could measure. She checked her work. Ford checked his instruments. They looked at another galaxy, then another, then dozens more. The result was the same each time, a quiet, persistent, undeniable flatness at the edges of galaxy after galaxy. Not an error, not an anomaly, a pattern, consistent and systematic, written across the rotation curves of spiral galaxies throughout the observable sky. There was only one reasonable interpretation. There had to be more mass than anyone could see. Mass distributed not just in the bright center, but spread outward, extending well beyond the visible disk of stars, filling a vast and invisible halo around each galaxy. A halo of something that exerted gravitational pull without emitting a single photon of light. Something that could not be seen, could not be photographed, could not be detected by any instrument then in existence, and yet was clearly, undeniably there, because the stars were moving in ways that nothing else could explain. Zwicky had seen the same shadow 40 years earlier, cast across the Coma cluster. Rubin saw it again, cast across the rotation curves of individual galaxies, one by one. The evidence was no longer a single eccentric observation from a single eccentric astronomer. It was a pattern. It was systematic. It was, as far as the data could tell, universal. The idea of dark matter, once dismissed, became something that could no longer be quietly set aside. And so the picture of the universe began, slowly, to change. What astronomers had been mapping for centuries, the stars, the nebulae, the galaxies, the great luminous structures of the cosmos, turned out to be a small fraction of what actually exists. A surface, a thin, bright skin stretched over something far larger and far darker. The numbers, when they eventually came into focus, were striking in their proportions. Ordinary matter, the kind that makes up everything you have ever touched, everything you have ever seen, every atom and every star that has ever burned. accounts for only about 5% of the total energy content of the universe. 5%. Protons, neutrons, electrons. Every planet, every ocean, every grain of dust drifting between the stars. Every galaxy that has ever been cataloged. Every nebula that has ever been photographed. Every photon of light that has ever crossed the sky. All of it, together, amounts to roughly 1 part in 20 of what the universe actually contains. Dark matter accounts for roughly 27%, more than 5 times as much as all the ordinary matter in existence. Not a small correction to the ledger, not a minor adjustment. A dominant component, present everywhere, shaping everything, and yet completely invisible to every telescope ever built. It does not glow. It does not absorb. It does not scatter light or emit radiation of any kind. It makes itself known only through gravity, through the way it bends the paths of stars and holds galaxies together and curves the fabric of space around it. That is the only language it speaks. And for a long time, no one was listening carefully enough to hear it. Rubin listened. She spent years at the telescope, measuring, checking, refining. She was not the only one, and the work was not hers alone. Science rarely belongs to a single person. But her observations, patient and precise, and repeated across dozens of galaxies, helped shift the weight of evidence past the point where it could be ignored. The flat rotation curves were real. The unseen mass was real. The universe was, in some fundamental sense, mostly dark. Dragonfly 44 sits at the far end of this story. It is not just a galaxy that contains dark matter, the way most galaxies do. It is a galaxy that is almost entirely dark matter, a structure in which the visible component, the stars, the ordinary baryonic matter, amounts to a fraction so small it barely registers. 1% of the stellar mass of the Milky Way, roughly 1 billion solar masses of stars, surrounded by roughly 1 trillion solar masses of something invisible. The ratio that Rubin glimpsed in the rotation curves of ordinary spiral galaxies, more dark than light, more unseen than seen, is taken here to an extreme that feels almost like a statement, as if the universe, in making Dragonfly 44, decided to show what it is mostly made of. Not stars, not light, not the bright, warm, familiar matter that we are built from and that we have always used to read the sky. Something else. Something older, perhaps, or at least something that came first, that settled into halos before the first star ever ignited, that provided the gravitational wells into which ordinary matter eventually fell, that made the galaxies possible in the first place. And in Dragonfly 44, that something else is almost all there is. The stars are there, faint and ancient, burning slowly at the edge of exhaustion. But they are guests. The dark matter was the host all along, and yet the dark matter itself remains unnamed in any deeper sense. We can measure its gravity. We can trace the curves it bends into space-time. We can count the globular clusters that orbit within its halo and work backward to its mass. But we cannot say what it is made of. Not yet. Not with any certainty. What we can say is what it is not. It is not the same as dark energy. Those two words, dark matter, dark energy, sit beside each other in the vocabulary of cosmology, and they are easy to blur together. But they are entirely separate things, pointing in entirely separate directions. Dark matter pulls. It gathers. It holds galaxies together and draws ordinary matter into its wells. Dark energy does the opposite. It pushes the universe apart, stretching the space between galaxies at an accelerating rate, working against gravity on the largest scales we can observe. Roughly 68% of the universe's total energy content belongs to dark energy. Dark matter accounts for roughly 27%, and all the ordinary matter, every star, every planet, every ocean, every atom, in every living thing, adds up to only about 5%. We are a small footnote in the universe's accounting. Dark energy and dark matter share only their obscurity. Beyond that, they are strangers to each other and to us. Dark energy is a property of space itself. As far as we can tell, a kind of pressure woven into the fabric of the universe, present even in perfect emptiness. Dark matter is something else. It has mass. It responds to gravity. It clusters in halos and shapes the architecture of everything visible. It behaves, in many ways, like matter, just matter that refuses to interact with light. That refusal is the heart of the mystery. Ordinary matter is, in a sense, loud. Protons and electrons interact with photons constantly, absorbing them, emitting them, scattering them. That is why we can see anything at all. Every color, every glow, every shadow is the story of ordinary matter and light in conversation. Dark matter has no such conversation. It does not emit light. It does not absorb light. It does not reflect it or scatter it or bend it through any electromagnetic interaction. Every kind of telescope ever built, optical, radio, infrared, X-ray, gamma ray, is, at its core, a device for collecting photons, and dark matter sends none. The only force it is known to exert is gravity. And possibly, the weak nuclear force, one of the four fundamental forces, the one responsible for certain kinds of radioactive decay. If dark matter interacts through the weak force, even faintly, then it might occasionally collide with an ordinary atomic nucleus and leave a tiny, measurable recoil. That possibility has driven decades of experiments. Deep underground laboratories, shielded from cosmic rays by kilometers of rock, have been built to listen for exactly that signal. Tanks of liquid xenon, cooled to near absolute zero, waiting in the dark for a single dark matter particle to brush against a single ordinary atom. So far, the silence has held. The leading candidate for many years has been something called a WIMP, a weakly interacting massive particle. The name describes what it would be: a particle with mass, interacting through the weak force, moving slowly enough to be cold dark matter in the cosmological sense. WIMPs were appealing partly because they emerged naturally from certain theories of particle physics that were developed for entirely separate reasons. The fact that those theories happened to predict a particle with roughly the right mass and interaction strength to explain dark matter seemed, to many physicists, like more than coincidence. It was called the WIMP miracle, but no WIMP has ever been directly detected. Experiment after experiment has pushed the sensitivity of detectors further, ruling out larger and larger regions of the parameter space where WIMPs might live. The silence is not proof that WIMPs do not exist. Absence of detection is not the same as absence. But the most straightforward versions of the WIMP hypothesis are under considerable pressure now, and the field has widened its search. There are other candidates. Axions are among them, extraordinarily light particles, originally proposed to solve a different problem in particle physics entirely, later recognized as plausible dark matter candidates. They would be so light and interact so weakly that detecting them requires a completely different class of experiment, devices that try to coax axions into converting into photons inside powerful magnetic fields. Some of those experiments are running now, listening at frequencies far below visible light, in the microwave range, for a faint signal that may or may not be there. Sterile neutrinos are another possibility. Ordinary neutrinos are already ghostly things. They pass through the Earth in vast numbers every second, barely interacting with anything. Sterile neutrinos would be heavier cousins that interact even less, coupling to ordinary matter only through gravity. They would be nearly impossible to detect directly, though certain X-ray observations have hinted, inconclusively, at their possible presence. And then there are primordial black holes. Not the black holes formed when massive stars collapse, but black holes that may have formed in the first fractions of a second after the Big Bang, when the universe was dense enough that random fluctuations in matter could have collapsed directly into black holes before any stars existed. If enough of them formed, and if they span the right range of masses, they could account for some or all of the dark matter. The detection of gravitational waves from merging black holes has renewed interest in this possibility, though the question remains open. What is striking is how many independent paths all lead to the same conclusion. Not to the same answer about what dark matter is, that remains unresolved, but to the same conclusion that something is there, the evidence does not rest on a single observation or a single method. It comes from many directions at once, each one using different instruments, different physics, different assumptions, and arriving at the same place. Galaxy rotation curves were the first systematic evidence, the flat lines that Vera Rubin traced across dozens of spiral galaxies, showing that stars at the outer edges orbit just as fast as stars near the center, which only makes sense if there is far more mass than the stars themselves provide. Gravitational lensing adds another voice. When light from a distant galaxy passes near a massive object, the mass bends the path of the light, distorting the image of whatever lies behind it. By measuring how much distortion occurs, astronomers can map the mass causing it, and repeatedly, the mass they find is far greater than the mass they can see. The dark matter reveals itself through the geometry of light, even though it produces none of its own. The cosmic microwave background speaks as well. That faint glow of ancient light, the afterglow of the Big Bang, carries within its subtle temperature variations the imprint of the early universe's density fluctuations. The precise pattern of those variations, measured with extraordinary care by satellites like Planck, is consistent with a universe in which cold dark matter was present from very early on, amplifying small overdensities into the seeds of everything that would later form. A universe without dark matter would have produced a different pattern. The pattern we observe fits the dark matter model with quiet precision. And then there is the large-scale structure of the universe itself. The way galaxies are distributed across hundreds of millions of light years, gathered into filaments and sheets, separated by vast, empty voids, matches the predictions of models that include dark matter with a fidelity that is difficult to dismiss. The cosmic web, as it is sometimes called, appears to be woven on a loom of dark matter, with ordinary matter tracing the threads. All of these lines of evidence are independent. They use different wavelength, different techniques, different theoretical frameworks, and yet they converge. That convergence is not proof in the mathematical sense. Science rarely offers that. But it is the kind of agreement that, in the quiet language of evidence, carries considerable weight. Dragonfly 44 sits within all of this. A single galaxy, faint and ancient, in a cluster 320 million light-years away. And yet it touches every thread of the dark matter story, the rotation curve logic, the lensing mass estimates, the globular cluster counts, the failed star formation, the halo that came first. It is not the whole story, but it is a place where the story becomes visible in its own dim and patient way. There is another way to weigh what cannot be seen. It does not require measuring the speed of stars. It does not require counting globular clusters. It uses something older and more fundamental: the fact that mass, any mass, bends the fabric of space around it. And when light travels through that bent space, its path curves. The light arrives at our telescopes from a slightly different direction than it would have otherwise. The source behind the mass appears distorted, stretched into arcs, sometimes into rings, sometimes into multiple ghost images of the same distant object. This is gravitational lensing. It was predicted by Einstein's general theory of relativity and confirmed during a solar eclipse in 1919, when stars near the edge of the sun appeared shifted from their true positions. The sun's gravity had bent their light. What works for a star works for a galaxy. What works for a galaxy works for a cluster of galaxies. The more mass, the stronger the lens. The stronger the lens, the more the background light is distorted. And so astronomers learn to read distortion as a map of mass. Not visible mass, not stars or gas or dust. Total mass, whatever is there, seen or unseen. When you measure how much a cluster of galaxies bends the light behind it, you are weighing the whole thing. Every proton, every electron, and, it turns out, a great deal of something else. The lensing maps rarely match the light maps. The places where the mass is concentrated, as revealed by the bending of light, are not always the places where the stars and gas are brightest. There is mass where there is little light. There is gravity without a visible source. This mismatch, seen across many clusters and many independent measurements, points quietly but persistently toward the same conclusion that rotation curves and globular cluster counts had already suggested. There is something there that we cannot see. One of the clearest demonstrations of this came from an event that astronomers were fortunate enough to observe in some detail. Two galaxy clusters, each containing hundreds of galaxies and vast clouds of hot gas, had passed through each other. The collision had happened long before anyone was watching. The light from it took hundreds of millions of years to reach us, but the aftermath was still visible, frozen in the sky, like the moment after a slow and enormous impact. This is the bullet cluster. When two clusters collide, the individual galaxies within them mostly pass through each other undisturbed. Galaxies are so small relative to the distances between them that direct collisions are rare. But the hot gas, the diffuse plasma that fills the space between galaxies and accounts for most of the ordinary matter in a cluster, does not pass through so easily. Gas interacts with gas. It slows, it heats, it glows in X-rays. And so the hot gas lagged behind. X-ray observations of the bullet cluster showed the gas concentrated in the middle, between the two clusters, compressed and superheated by the collision. That is where the ordinary matter ended up, slowed, piled together, radiating. But the gravitational lensing told a different story. The lensing map showed the mass concentrated not in the middle, not where the gas was, but out to the sides, ahead of the gas, in the direction each cluster had been traveling. Something had kept moving. Something had passed through the collision without slowing down, without interacting, without caring that another cluster was in the way. The mass and the gas had separated. In a universe without dark matter, this should not happen. If ordinary matter is all there is, then the gas is where the mass is. The two should overlap, but they did not. The mass had sailed through the collision while the gas had stalled. Whatever carried most of the mass had no trouble passing through another cluster of galaxies. It did not interact. It did not slow. It simply continued on its way, indifferent. This is what dark matter does. It does not collide in the way ordinary matter does. It does not radiate. It does not compress. It passes through. And in the bullet cluster, that behavior left a visible signature, a separation between where the mass was and where the light was, written in the distorted shapes of galaxies far behind the collision. It is, as far as we can tell, one of the most direct pieces of evidence we have. Not a rotation curve, not a velocity dispersion, not a count of globular clusters, a collision, observed in two different wavelengths, showing mass and matter going their separate ways. The dark matter halo of each cluster had passed through the other's halo like two ghosts walking through the same wall, while the ordinary matter, the gas, the plasma, the stuff that interacts, had piled up between them. And this is what dark matter appears to do everywhere, not just in collisions. It forms halos, large, roughly spherical structures of invisible mass that surround and envelop galaxies and galaxy clusters. These halos are not incidental. They are not a side effect. They appear to be the primary structure, the thing that formed first, the gravitational well into which ordinary matter later fell. In the early universe, shortly after the Big Bang, matter was distributed almost uniformly. Almost. There were tiny fluctuations, regions slightly denser than average, regions slightly less dense. In a universe of only ordinary matter, those fluctuations would have been smoothed out by the pressure of radiation before they could grow into anything. The universe would have remained nearly featureless. No galaxies, no stars, no slow accumulation of gas into the structures we see today. But dark matter does not interact with radiation in the same way. It does not feel that smoothing pressure. And so the dark matter fluctuations were free to grow, even in the early universe, pulling more dark matter toward them, deepening their gravitational wells, building halos long before the first star ever ignited. By the time ordinary matter was free to move, after the universe had cooled enough for electrons and protons to combine into neutral hydrogen, the dark matter halos were already waiting. Ordinary matter fell into them. Gas flowed along the gravitational contours that dark matter had already carved. It pooled in the centers of halos. It cooled. It condensed. It collapsed under its own weight into the first stars, the first galaxies, the first faint lights in an otherwise dark universe. The dark matter did not make the stars, but it made the places where stars could form. Without those halos, the gas would have had nothing to fall into. The fluctuations in ordinary matter alone were too small, too easily disrupted, to have grown into galaxies on their own. The universe we observe, with its hundreds of billions of galaxies, its filaments and clusters and voids, required a scaffold, something to hold the shape while the ordinary matter settled. Dark matter provided that scaffold quietly, invisibly, before any light existed to reveal it. Dragonfly 44 is a remnant of that process. Its dark matter halo formed in the early universe, as halos do. Ordinary matter began to fall in, stars began to form, and then, for reasons that are still not fully understood, the process slowed, stopped. The halo remained, enormous, ancient, patient, while the stars it managed to produce were few and faint and old. What was left is what we see today. A galaxy the size of the Milky Way, held together by 1 trillion solar masses of invisible matter, lit by only 1 billion solar masses of stars, a structure that is almost entirely dark, drifting in a cluster 320 million light-years away. Its halo intact, its star formation long since ended, its light so faint that it hid from us entirely until a small array of camera lenses happened to look in the right direction. We know this not only from what we observe directly, but from what we can simulate. When astronomers build models of the universe, vast computational recreations that begin with the conditions just after the Big Bang and let physics run forward, they find something striking. If those simulations include dark matter, the structures that emerge match what we actually see. Filaments of galaxies stretching across hundreds of millions of light years, clusters where those filaments intersect, great empty voids between them, quiet and hollow. The whole intricate web of the cosmos, reproduced with quiet accuracy, simply by including something invisible. Remove the dark matter from those simulations, and the web collapses. The filaments blur, the clusters thin. The universe that emerges looks nothing like the one we live in. That agreement between simulation and observation is one of the reasons dark matter is taken so seriously. It is not a single anomalous measurement. It is a thread that runs through everything we know about how the universe is shaped. And yet, Dragonfly 44 sits at the edge of what those simulations predict. Its halo is there, enormous and ancient, exactly as the models would expect. But the galaxy inside that halo is almost nothing, a whisper where there should have been a voice. Something interrupted the process. The question is what? There are several possibilities, and astronomers hold them gently, without certainty, because the evidence does not yet point clearly to any one of them. Each hypothesis is plausible. Each is supported by some observation, somewhere, and each describes a different kind of failure, a different way a galaxy can almost happen, and then not quite. The first possibility has to do with the environment Dragonfly 44 finds itself in. The Coma Cluster is not a quiet place. Over 1,000 galaxies occupy a region of space that, on cosmic scales, is remarkably compact. Galaxies pass near one another. Their gravitational fields reach outward, pulling and stretching at whatever lies close. This process, tidal stripping, astronomers call it, can peel material away from a galaxy the way a current pulls at the edge of a river. Gas is particularly vulnerable. It is diffuse, loosely bound, spread across a galaxy's outer regions. When a neighboring galaxy passes close enough, its gravity can draw that gas away before it ever has the chance to collapse and cool and form stars. The gas simply leaves, pulled into the space between galaxies, or absorbed by something larger, or dispersed so thoroughly that it can never reassemble. If this happened to Dragonfly 44 early enough, if the Coma Cluster's tidal forces stripped away its gas reservoir before star formation could truly take hold, then the galaxy's emptiness is not a failure of its own making. It is a consequence of where it ended up. A structure that might have been luminous had it formed somewhere quieter, somewhere with more room. There is something almost melancholy in that idea. A galaxy shaped by its neighbors, diminished by proximity, left with only the stars it managed to form before the stripping began. But there is a second possibility, and it points inward rather than outward. When the very first stars form inside a dark matter halo, they are not gentle. The earliest stars in the universe were massive, far more massive than most stars that form today, and they burned intensely, briefly, and then ended in enormous explosions. Those explosions released energy, not just light, but shock waves, winds of particles moving outward at tremendous speed, pushing against the gas that surrounded them. This is called stellar feedback, and in a small or fragile system, it can be catastrophic. If the first generation of stars in Dragonfly 44 was massive enough, their collective energy output, their radiation, their stellar winds, their eventual supernovae, may have been sufficient to drive most of the remaining gas out of the galaxy entirely, not stripped by a neighbor, but expelled from within. The galaxy's own first stars, in the act of being born and dying, may have prevented most of the stars that would have followed them. It is a strange kind of self-limiting process. A galaxy that briefly ignites, and in igniting, extinguishes itself. The first stars consuming the fuel that would have fed the next generation, leaving behind only their own faint descendants and a halo that had expected to hold far more. This hypothesis is harder to test directly. The stars responsible would be long gone, their lives measured in millions of years, not billions. What remains is only the aftermath, the quiet, the emptiness, the old red stars drifting slowly through a halo that once held so much more potential. And then there is a third possibility, quieter still, and in some ways the most elegant. Dark matter halos do not simply sit still, they rotate. The angular momentum of a halo, the spin it carries from the turbulent conditions of its formation, influences how the gas inside it behaves. In most halos, the spin is moderate enough that gas can gradually lose energy, cool, and sink toward the center where it forms a dense disk. That disk becomes the birthplace of stars. But if a halo spins too fast, the gas cannot settle. The centrifugal effect, the tendency of rotating material to resist falling inward, keeps the gas spread out, diffuse, unable to reach the densities needed for star formation to begin. The gas remains suspended, orbiting, never collapsing. And without collapse, there are no stars. In this scenario, Dragonfly 44's emptiness is not the result of loss. Nothing was taken away. The gas may still be there, in some form, or may have slowly dispersed over billions of years. But it never had the chance to become stars, because the geometry of the halo itself worked against it. The spin was simply too high. The conditions were never right. A halo that contained everything necessary and still produced almost nothing. These three hypotheses are not mutually exclusive. Tidal stripping, stellar feedback, and excessive spin could each have played a role, in different proportions, at different moments in Dragonfly 44's history. The universe rarely has a single cause for anything. What we observe is usually the result of many processes, layered over billions of years, each leaving only a faint trace. What all three hypotheses share is this. They describe a dark matter halo that formed as expected, that drew in ordinary matter as expected, and that then, through some combination of circumstance and physics, failed to convert that matter into the luminous, star-rich galaxy the halo's mass would have predicted. The halo is not unusual. Halos of that size exist throughout the universe, and most of them host galaxies far brighter than Dragonfly 44. What is unusual is the outcome, the disproportion, the vast, invisible structure surrounding so little light. And that disproportion is what makes Dragonfly 44 worth studying so carefully. It is not just a curiosity. It is a test case, a place where the normal relationship between dark matter and star formation broke down, and where the reasons for that breakdown, if we can find them, might tell us something fundamental about how galaxies form and how often they fail. The universe, it turns out, may contain many such failures. Halos that formed, drew in gas, and then went quiet. Structures that are present, gravitationally real, but dark. Patient, waiting for nothing in particular. Dragonfly 44 is one we happen to find. And yet, Dragonfly 44 is not alone. That is perhaps the quieter revelation. Not just that one such galaxy exists, but that the universe appears to be filled with them. Structures like it, dim, spread thin, held together mostly by something we cannot see. Once astronomers knew what to look for, they began finding them everywhere, and the count has not stopped rising. Ultra-diffuse galaxies turn up in two very different kinds of places. Some live inside dense galaxy clusters, surrounded by hundreds of neighbors, embedded in the gravitational chaos of some of the most crowded environments in the universe. Others are found in relative isolation, drifting through quieter regions of space, far from any cluster, with no obvious companion to disturb them. That difference in location matters. It suggests that there is not one single story behind these galaxies. There may be several. For the ones living inside clusters, astronomers have a plausible account. A galaxy enters a dense cluster environment, and the cluster is not gentle. The gravitational tides generated by so much mass pulling in so many directions can reach into a galaxy and pull material away from it, slowly, over billions of years. But persistently, gas is stripped. Stars that would have formed never do. The outer regions of the galaxy are drawn off, leaving behind something more diffuse, more spread out, dimmer than it once was. This process is called tidal stripping, and it is not hypothetical. There is evidence of it happening across many galaxy clusters. Streams of stars trailing behind galaxies like long, faint scarves. Material caught between galaxies, belonging fully to neither. The cluster environment is, in a sense, erosive. It wears things down. Some ultra-diffuse galaxies and clusters may have begun as ordinary galaxies, galaxies with normal stellar densities, normal brightness, normal proportions of dark matter and stars. And then, over time, the cluster worked on them, stripped away their outer layers, left them hollowed out, or at least thinned. What we see now is a remnant, a galaxy that was once something else, and has been slowly, quietly undone. There is something almost geological about that image. The way a river carves a canyon, not in a single moment, but across an immensity of time, wearing away stone grain by grain. A galaxy entering a cluster and emerging, billions of years later, as something barely recognizable. But then there are the isolated ones. And they present a different problem entirely. A galaxy drifting alone in a relatively empty region of space has not been inside a cluster. There are no tidal forces of that magnitude to blame. No neighboring galaxies close enough to strip away its gas. Whatever it is, it arrived that way, or became that way through some internal process, some failure of its own star formation that had nothing to do with its surroundings. These isolated ultra-diffuse galaxies cannot be explained by stripping. They must have formed with low stellar density from the beginning. Their dark matter halos may have spun too fast, or their early star formation may have been quenched by some internal feedback before it could take hold. The details are still being worked out, but the implication is clear: there is more than one way for a galaxy to end up dim. The existence of both kinds, cluster-dwelling and isolated, tells astronomers that ultra-diffuse galaxies are not a single phenomenon with a single cause. They are a category defined by what they look like, not by how they got there. And that makes them harder to understand, but also more interesting. They are a symptom of several different things that can go wrong, or perhaps go differently, in the long process of galaxy formation. Within the Coma cluster alone, the same dense collection of galaxies where Dragonfly 44 lives, the same cluster where Fritz Zwicky first noticed something was missing nearly a century ago. Astronomers have now identified hundreds of ultra-diffuse galaxies. Hundreds. In a single cluster. Most of them were discovered only in the past decade. They were always there, presumably, drifting through the cluster, faint and spread thin, invisible to surveys that were not designed to find them. It took new instruments, new techniques, new ways of looking at the sky with sensitivity to low surface brightness before they began to appear. And the Coma cluster is not special in this regard. It is simply one of the better studied clusters, close enough and well observed enough that its population of ultra-diffuse galaxies has been cataloged with some care. Other clusters, examined with similar sensitivity, reveal similar populations. Hundreds of these dim, diffuse structures orbiting within the gravitational well of the cluster, mostly invisible to older surveys. The census is still incomplete. Even in the Coma cluster, with all the attention it has received, astronomers are confident they have not found all of them. The faintest ones remain below the detection threshold of current instruments. They are there, in all likelihood, present, gravitationally real, simply too dim to register. And if the Coma cluster contains hundreds, and other clusters contain hundreds, and clusters are distributed across the observable universe in their thousands, then the total number of ultra-diffuse galaxies across the cosmos may be very large indeed. Roughly, as far as current estimates suggest, the number could be in the hundreds of billions. Hundreds of billions of galaxies so faint they were essentially invisible to astronomy until recently. Structures the size of the Milky Way or larger, containing almost no stars, held together by dark matter, drifting through clusters or through quieter regions of space, patient and dim, leaving almost no trace on the light that reaches our telescopes. That number is worth sitting with for a moment. The observable universe contains something in the range of 2 trillion galaxies. By recent estimates, if hundreds of billions of those are ultra-diffuse, if a significant fraction of all galaxies are structures that barely shine, then the visible universe is even less representative of what is actually out there than astronomers had previously thought. We look up at the sky and we see light. We see bright spirals and glowing ellipticals, and the long arcs of lensed galaxies bending around massive clusters. And we have built our understanding of the universe largely from that light, from what shines. But the universe does not seem to have organized itself around what is easy to see. It has organized itself around gravity, around dark matter, around halos that formed in the early universe and drew in whatever ordinary matter happened to be nearby. And in many cases, perhaps in a very large number of cases, that ordinary matter never became much, never collapsed into dense, bright, star-forming regions, never lit up. The light we see may be, in some sense, the exception, not the rule. Dragonfly 44 was one galaxy, found almost by accident, by a small array of camera lenses pointed at a patch of sky in the Coma cluster. And what it opened up was not just a question about one unusual galaxy, but a question about the universe as a whole, about how many structures like it exist, about how much of what is real out there has simply never announced itself with light. The answer, as best as we can currently tell, is a great deal. A great deal of the universe is quiet in this way, present, massive, shaped by the same physics that shaped everything else, but dark, spread thin, carrying within it the ancient record of a star formation that barely began and then stopped. Hundreds of billions of galaxies, drifting, each one a dark matter halo with a handful of old stars at its center, or perhaps no stars at all, each one invisible to most of the instruments we have built, each one patient in the way that only very old, very quiet things can be patient. And we are only just beginning to find them. The census we have of these faint, spread-thin galaxies is still deeply incomplete. Even in the Coma cluster, one of the most studied galaxy clusters in the sky, observed for decades by some of the most powerful instruments ever built, astronomers are still finding ultra-diffuse galaxies they had simply never noticed before. Not because the galaxies weren't there. They were always there. but because the tools we built were not designed to see them. Most telescopes are optimized for brightness, for compact, concentrated sources of light. A quasar blazing across billions of light years, a spiral galaxy with its tight, luminous core. These are the things large telescopes were built to find, and they find them well. But a galaxy like Dragonfly 44, spread across 60,000 light years, its light diluted almost to nothing, simply doesn't register the way those objects do. It falls below the threshold. It blurs into the background. It looks, to most instruments, like noise. And so for a long time, it was treated as noise. This is part of what makes the Dragonfly telephoto array so unusual. It was not built to be the most powerful telescope in the world. It was built to be the most sensitive to faint, diffuse light, and those are not the same thing at all. The design of the array is careful in a very specific way. Large telescopes, for all their power, scatter light internally. Light enters the optics, bounces off surfaces, reflects off edges, and creates a kind of soft glow that spreads across the detector. For bright objects, this doesn't matter much. But for something as faint as an ultra-diffuse galaxy, that internal scattered light can completely overwhelm the signal you're trying to measure. The galaxy you're looking for is dimmer than the noise your own instrument is generating. The Dragonfly array addresses this by using small telephoto lenses, the kind originally designed for photography, with specialized coatings that suppress internal reflections to an extraordinary degree. Each lens contributes a clean, low-scatter image. And because the array uses many lenses working in parallel, pointing at the same patch of sky, the signal from faint diffuse sources builds up while the noise averages down. It is a quiet, methodical approach, patient in its own way. The array takes its name from the compound eye of a dragonfly. A dragonfly does not see the world through a single large lens. It sees through hundreds of small facets, each gathering light from a slightly different angle, each contributing to a wide and sensitive picture of the world. The Dragonfly array works on a similar principle, not one large mirror, but many small lenses, each doing its part, together building an image that no single lens could produce alone. There is something fitting about that. A galaxy made almost entirely of invisible matter, found by an instrument named after an insect's eye, both of them sensitive to things that others miss. But finding Dragonfly 44 in an image was only the beginning. Seeing a faint smudge of light in a photograph tells you that something is there. It tells you roughly where it is, roughly how large it appears, roughly how bright. What it does not tell you is how much that object actually weighs, how much mass is moving inside it, how fast its stars are traveling, whether the gravity holding it together is consistent with what you can see. For that, you need spectroscopy. Follow-up observations of Dragonfly 44 were carried out using the Deimos spectrograph at the Keck Observatory on the summit of Mauna Kea in Hawaii. Keck is among the largest optical telescopes in the world. Its primary mirror spans 10 meters, a surface so large that it had to be built from 36 hexagonal segments, each one precisely aligned to act as a single continuous mirror. Even with an instrument of that scale, measuring the internal motions of Dragonfly 44 was not straightforward. The challenge is the stars, or rather, the scarcity of them. In a galaxy like the Milky Way, there are hundreds of billions of stars. When you point a spectrograph at it, you are collecting light from an enormous number of sources simultaneously. The signal is strong. The measurement is relatively clean. Dragonfly 44 has perhaps 1% as many stars. The light it offers is thin, faint, spread across a large area of sky, with very little concentrated anywhere. To measure the velocity dispersion of those stars, to determine how fast they are moving relative to one another, the telescope had to collect that faint light for many hours. Integration time, astronomers call it. The longer you observe, the more photons you accumulate, and the more clearly the signal emerges from the background. For Dragonfly 44, this meant long nights of observation, the great mirror of Keck gathering light from a galaxy that barely wanted to be seen. What the spectrograph measures, in essence, is the Doppler shift of starlight. Stars moving toward us have their light compressed slightly toward the blue end of the spectrum. Stars moving away have their light stretched slightly toward the red. In a galaxy where stars are orbiting through a gravitational field, some are always moving toward us and some away, and the spread of those velocities, the velocity dispersion, tells you how deep the gravitational well is, how much mass is pulling on those stars from all directions. The velocity dispersion measured for Dragonfly 44 was approximately 47 kilometers per second. That number, on its own, means little. But when you compare it to the number you would expect from a galaxy with only 1 billion solar masses of stars, the answer is striking. The stars are moving far too fast. The gravitational well they are orbiting through is far deeper than the visible matter could possibly create. Something else is there. Something massive. Something that contributes enormously to the gravity of this place without contributing a single photon of light. This is how dark matter announces itself. When it announces itself at all, not by being seen, but by the motion it causes in the things that can be seen. The stars of Dragonfly 44 are like leaves on the surface of a river. You cannot see the water moving beneath them, but you can watch the leaves, and from the way they move, you can infer the current. The current in Dragonfly 44 is vast, far larger than the leaves would suggest. And so the picture that emerged from those long nights at Keck was a strange and quiet one. A galaxy the size of the Milky Way. A galaxy with barely enough stars to fill a small corner of what it occupies. A galaxy whose mass is almost entirely invisible, almost entirely dark, almost entirely composed of something we have never directly touched or measured or identified, only inferred again and again from the way it bends and pulls and holds. Roughly 99.99% of Dragonfly 44's total mass is dark matter. That number is worth sitting with for a moment. Of everything that makes up this galaxy, every particle, every gravitational influence, every structure that has persisted across billions of years, only a tiny fraction is the kind of matter that can shine. The rest is dark, has always been dark, will remain dark long after the last of those old red stars has quietly exhausted itself and gone cold. Dragonfly 44 is not a galaxy that lost its light. It is a galaxy that never had much light to begin with. A dark matter halo that gathered just enough ordinary matter to form a sparse scattering of stars, and then, for reasons we are still working to understand, stopped. We know this not from seeing the dark matter directly, but from listening to the stars that remain. Those stars, sparse as they are, move, and the way they move tells a story. When astronomers turned the Keck Observatory toward Dragonfly 44 and measured the velocities of its stars, they found something that could not be explained by the stars alone. The stars were moving at roughly 47 kilometers per second. That is not a gentle drift. That is a sustained, deep motion, the kind of motion that requires an enormous gravitational well to sustain it. If you were to calculate how much mass would be needed to keep those stars from flying apart, to hold that galaxy together against its own internal motion, the number you would arrive at is far, far greater than the mass of the stars themselves. The stars account for almost nothing in that calculation. Something else is doing the holding, something vast and invisible, pressing inward from all sides, keeping the whole structure from dissolving into the surrounding dark. That something is the halo. And to understand the halo, it helps to go back, not just to the beginning of Dragonfly 44, but to the beginning of structure itself. In the very early universe, shortly after the Big Bang, the cosmos was nearly uniform. Nearly, but not quite. There were tiny variations in density, regions that were, by the smallest of margins, ever so slightly more concentrated than their surroundings. Those variations were subtle enough that you could have passed through them without noticing anything at all. But dark matter noticed. Dark matter, moving slowly and responding only to gravity, began to drift toward those denser regions. Over millions of years, and then hundreds of millions of years, it gathered, it pooled, it formed structures, halos, that grew heavier and more gravitationally dominant with time. And as those halos deepened, ordinary matter began to fall into them. Gas clouds, drawn by gravity, descended into the dark matter wells. They compressed, they cooled, and in some of those halos, under the right conditions, the gas grew dense enough to ignite. Stars were born. This is, as far as we can tell, how most galaxies came to be, not as islands of light that formed on their own, but as ordinary matter that fell into pre-existing dark matter scaffolding. The dark matter came first, the light came after, and only where conditions allowed. Dragonfly 44 had the scaffolding, it had the halo, but for reasons that remain genuinely uncertain, the light never fully arrived. And this raises a quieter, stranger possibility. If dark matter halos form first, if they are the primary structures around which everything else organizes, then there is no particular reason why every halo should eventually produce stars. Some halos may have gathered their dark matter, settled into stable configurations, and then simply waited, while the gas that might have formed stars never arrived, or arrived and was lost, or never cooled enough to collapse. Those halos would be invisible, not faint, not dim. Invisible in the most complete sense. No stars, no gas glowing in any wavelength, no signal of any kind that any telescope we have ever built could detect. They would be drifting through the universe right now. Structures with real mass, real gravitational influence, real presence in the fabric of space, and yet entirely beyond our reach. The smallest dark matter halos are thought to be particularly prone to this. A halo with relatively little mass may simply never have been able to hold on to enough gas to form even a single star. The gas would have been too warm, too easily dispersed, too easily stolen by the gravitational pull of larger neighbors. And so the halo would persist, dark and patient, with nothing inside it that could ever announce its existence. How many of these purely dark structures might exist is not something we can currently say with confidence. The honest answer is that we do not know, and we have no direct way of finding out. They leave no light. They leave no trace in any spectrum. They can only be inferred, statistically, from the way large-scale structure behaves, from subtle distortions in the distribution of galaxies, from the way light bends as it passes through regions that appear to be empty. It is a strange kind of knowledge, knowing that something is probably there in large numbers, while having no way to point at any single one of them and say, there. And yet the evidence for their existence is woven into something we can observe, something that has been traveling toward us for nearly 14 billion years. The cosmic microwave background is the oldest light in the universe. It is the afterglow of a time when the cosmos was so hot and dense that light could not travel freely, when every photon was immediately absorbed and re-emitted, over and over, in a fog of plasma that filled all of space. And then, roughly 380,000 years after the Big Bang, the universe cooled just enough for electrons and protons to combine into neutral hydrogen. The fog cleared, and the light that had been trapped inside it streamed outward in every direction. That light is still traveling. It has been traveling ever since. Stretched by the expansion of the universe into microwave radiation, it now arrives at our instruments as a faint, nearly uniform glow coming equally from every point in the sky. Nearly uniform. Embedded within that glow are tiny temperature variations, fluctuations of about 1 part in 100,000, that map the density variations of the very early universe. The slightly denser regions, the slightly emptier ones, the seeds of everything that would eventually form. And those fluctuations carry the imprint of dark matter. Dark matter, because it does not interact with light, was already clumping in the early universe while ordinary matter was still locked in that hot, luminous fog. It was already beginning to build the halos that would later gather gas and stars. The density variations encoded in the cosmic microwave background are not just a record of where ordinary matter was concentrated. They are a record of where dark matter had already begun to pull. When we measure the cosmic microwave background with precision, as the Planck satellite did, mapping the entire sky with extraordinary sensitivity, The pattern we find is consistent with a universe in which dark matter is cold, meaning it moved slowly in the early universe, clumping readily under gravity rather than streaming away from dense regions. Cold dark matter settling into halos, building the scaffolding that ordinary matter would later inhabit. The pattern fits. The simulations that include cold dark matter reproduce the large-scale structure of the universe, the filaments, the voids, the clusters, with a fidelity that is difficult to explain any other way. And so we arrive at a picture of the universe that is, in its quiet way, rather humbling. The structures we can see, the galaxies, the clusters, the great webs of light that span hundreds of millions of light years, are, in a sense, the surface of something much deeper. They are the places where ordinary matter happened to fall into dark matter halos and happened to form stars. They are the lit windows in a vast, mostly dark building. The building itself is dark matter, and most of its rooms have no windows at all. Dragonfly 44 is one of the rare rooms where a few small lights were left on. Not many, not bright, but enough to be found 320 million light years away by a small array of camera lenses pointed at a patch of sky that most surveys had quietly passed over. Enough to tell us something about all the rooms we cannot see. There is a word that cosmologists use for the dark matter in our models: cold. It does not mean cold the way a winter morning is cold. It means something more precise, and in its own way, more serene. It means that in the early universe, dark matter particles were moving slowly, not racing outward in all directions, not scattering and dispersing, but drifting, gently, settling into the shallow gravitational wells that the universe had prepared for them. The Planck satellite, a spacecraft that spent years mapping the faint afterglow of the Big Bang with extraordinary care, returned measurements consistent with exactly this picture. The subtle temperature variations written across that ancient light, the cosmic microwave background, carry within them the fingerprints of density fluctuations from the universe's first moments. And those fingerprints match a universe in which dark matter was cold, slow-moving, prone to clumping. This matters because cold dark matter behaves in a particular way over time. It does not form one vast structure all at once. It builds from the bottom up. Small halos condense first, drawn together by their own gravity. Then those small halos find each other and merge. And the merged structures find others and merge again. Over billions of years, this patient accumulation builds larger and larger halos, the great scaffolding into which ordinary matter eventually falls, and from which galaxies are born. It is a slow architecture, a quiet one, like sediment settling into layers over geological time, each layer pressing gently on the one below. And within this picture, Dragonfly 44 presents something of a puzzle. Its dark matter halo is enormous, roughly 1 trillion solar masses, as best as measurements allow us to say. That is a halo consistent with a galaxy far larger and far brighter than anything Dragonfly 44 actually is. A halo of that size, and the standard picture of cold dark matter, should have drawn in vast quantities of gas over billions of years, should have given rise to hundreds of billions of stars, should, by now, be a luminous and substantial galaxy, visible from great distances without any special instrument. And yet, what sits inside that halo is a whisper, roughly 1 billion solar masses of stars, about 1% of what the Milky Way contains, scattered so thinly across 60,000 light years that the galaxy was invisible to most surveys that had looked directly at it. Even among ultra-diffuse galaxies, themselves already outliers, already the faint and ghostly edge cases of the galaxy population, Dragonfly 44 is an extreme. Its ratio of dark matter to stars is not merely unusual, it is, as far as we can tell, among the most extreme ever measured for any galaxy of its size. A halo built for a giant inhabited by almost nothing. This is what led some researchers to reach for a new kind of language. They began to call it a failed galaxy. The phrase carries a certain weight, Not failure in any moral sense, not failure as something gone wrong, but failure in the way that a seed can fail to become a tree, not because anything was broken, but because the conditions at some critical moment did not align. The ingredients were present. The halo was there, deep and massive, waiting. But the gas did not settle, or was stripped away, or was expelled by the first brief generation of stars before it could give rise to a second. And so the process stopped. What remained was the halo, patient, invisible, holding its shape across billions of years, and within it, a sparse population of old stars, the remnants of that one early episode of formation, slowly aging in the dark. The concept of a failed galaxy is, in its quiet way, a challenging one. For a long time, the working assumption in cosmology was that dark matter halos and galaxies were, in some deep sense, paired. A halo of sufficient mass would, given enough time, become a galaxy. The dark matter would gather the gas would cool and collapse, the stars would form. It was understood to be a process with many variables, many possible outcomes in terms of size and shape and brightness, but a process that, for halos above a certain mass threshold, would reliably produce something luminous. Dragonfly 44 suggests that this assumption may need to be held more loosely. Here is a halo that, by its mass, should have crossed that threshold comfortably. A halo that, in the cold dark matter picture, had every reason to become a large and ordinary galaxy. And it did not. It produced a thin scattering of stars and then, apparently, stopped, leaving behind a structure that is 99.99% dark matter, drifting through the coma cluster like a ghost of something that never quite arrived. If Dragonfly 44 could fail, the question follows naturally. How many others did? Not the small halos, the ones below the threshold where star formation becomes difficult regardless. Those have long been expected to be dark. But halos like this one, large halos with mass enough to have built something grand. How many of them are drifting through the universe right now, carrying almost no stars, invisible to every survey that was not specifically designed to look for the faintest possible light? The honest answer is that we do not know. The census of ultra-diffuse galaxies is still deeply incomplete, even in the Coma Cluster, which is one of the most studied galaxy clusters in the sky. Most of the ultra-diffuse population was only discovered in the past decade. Across the broader universe, the number of such objects may be in the hundreds of billions, and the fraction of those that are as extreme as Dragonfly 44, as dark, as dominated by invisible mass, remains an open question. What we can say is that the universe appears to be more comfortable with failure, in this quiet sense, than the earlier models assumed. The building has more dark rooms than we thought. Not just the small closets of the tiny halos, the ones too modest to ever have gathered much gas, but large rooms with high ceilings, rooms that were built for light and never received it. Dragonfly 44 is one of those rooms. And there is something in that which settles gently, if you let it. The universe does not insist on luminosity. It does not require that every structure it builds become visible, become active, become something that announces itself across millions of light years. It is content, apparently, to build in the dark, to assemble halos of enormous mass and leave them quiet, to let the ingredients gather and then simply hold. There is no urgency in any of this. The halo of Dragonfly 44 has been drifting through the Coma Cluster for billions of years. It is not waiting for anything. It is not becoming anything. It simply is a vast, cold, invisible architecture carrying within it a small inheritance of ancient starlight, and otherwise asking nothing of the universe at all. Cold, dark matter, moving slowly, building from the bottom up, patient beyond any human measure of patience. And somewhere within it, a billion suns, old and red and fading, each one a remnant of a moment when something almost happened. And if Dragonfly 44 is not alone in this, if there are others like it, halos that gathered their mass, held their shape, and then simply never filled with light, then the universe we think we know may be only a small fraction of the universe that actually exists. Not a small fraction in terms of space, but in terms of structure, in terms of the number of things that were built and never seen. Consider what the simulations suggest. When astronomers run detailed models of how the universe evolved, feeding in the known physics of gravity, dark matter, gas, and time, those models predict a very large number of dark matter halos, far more than the number of visible galaxies we observe. The models expect halos by the billions, small ones, medium ones, halos that should, in principle, have gathered enough ordinary matter to form at least some stars. And yet, when we look at the sky, the galaxies are not there. This is not a small discrepancy. It is a persistent one, noticed decades ago, studied carefully, and still not fully resolved. Astronomers gave it a name: the missing satellites problem. The name comes from the context in which it was first clearly described. Simulations of a galaxy like the Milky Way predict that it should be surrounded by hundreds of smaller satellite galaxies, each nestled within its own dark matter halo, orbiting in the outer reaches of our galaxy's gravitational influence. But when astronomers counted the actual satellites of the Milky Way, they found far fewer. Dozens, not hundreds. The halos, according to the models, should be there. The galaxies inside them are not. For a long time, this felt like a problem with the models. Perhaps the simulations were wrong. Perhaps dark matter did not behave quite as assumed. Perhaps the physics needed adjusting. But another possibility, quieter and in some ways more unsettling, is that the models are roughly correct, and the halos really are there, simply dark, simply empty of stars. Most small halos, on this view, never formed enough stars to be visible. The gas fell in, or perhaps it never fell in at all. The conditions for star formation were never quite met. The threshold was never crossed, and so the halo persists, invisible, carrying its mass through the universe without ever announcing itself. There would be no way to find such a halo directly, no light to detect, no radio waves, no infrared glow, no X-ray emission, nothing that any telescope of any design could register. The only trace would be gravitational, a subtle bending of light from more distant objects, a faint statistical signature in the large-scale distribution of matter, clues that require enormous care to interpret, and that even then speak only in probabilities. And yet, the ratio of dark matter halos to luminous galaxies is already known to be high, even setting aside the smallest structures. Even among halos large enough that we might expect them to host a visible galaxy, many appear to host nothing at all, or nothing we can detect. The universe, it seems, builds far more containers than it fills. Dragonfly 44 sits at a particular place within this picture. It is not one of the smallest halos. Its total mass, roughly 1 trillion times the mass of the Sun, is comparable to the halo of the Milky Way. It is not a marginal structure. It is, by the measure of dark matter, a substantial one. And yet, it produced only about 1 billion solar masses of stars, 0.1% of what a galaxy of its halo mass might ordinarily be expected to form. This is what makes it so unusual, even among ultra-diffuse galaxies. It is not a small halo that barely flickered. It is a large halo that barely flickered. Some researchers think of it as the high-mass end of a continuous population, a spectrum of structures that ranges from completely dark halos at one extreme, through ultra-diffuse galaxies like Dragonfly 44 in the middle, to ordinary luminous galaxies at the other end. On this view, Dragonfly 44 is not an anomaly so much as a boundary case, a halo just massive enough, just dense enough, just fortunate enough in its early conditions to have crossed the threshold into star formation, but only barely and only briefly. The stars it made are old. They formed early, in the first few billion years of the universe's life. when the conditions were perhaps slightly more favorable, when the gas had not yet been entirely lost or heated or expelled, and then star formation stopped, the window closed, and what remained was what we see today, a sparse field of ancient, reddening suns slowly cooling within a vast dark envelope. Below Dragonfly 44 on that spectrum, there may be halos of similar or even greater mass that never crossed the threshold at all. Halos that gathered everything they needed and still produced nothing visible, nothing that a telescope could find, nothing that would appear in any catalog, any survey, any map of the known universe. How many such structures exist is genuinely unknown. The honest answer is that we do not know how to count them. We can estimate, based on simulations and on the statistics of what we do observe. We can reason about what the missing satellites problem implies. We can note that the discrepancy between predicted halos and observed galaxies grows larger as we look at smaller and smaller scales. But the dark halos themselves remain beyond reach. They are not hypothetical in the sense of being doubted. The gravitational evidence for dark matter is strong enough, and the simulations consistent enough that most astronomers consider the existence of dark halos to be well supported. They are hypothetical only in the sense that we cannot point to any one of them and say, there. There is something in this that asks for a certain kind of patience in the mind. The universe is not obligated to make itself legible to us. It did not arrange its structures so that they would be visible to creatures who evolved on a small planet around an ordinary star. It built what the physics required, and the physics, apparently, required a great deal of darkness. What we can see, the galaxies, the clusters, the filaments of light stretching across hundreds of millions of light years, may be, in some sense, the surface of a much deeper architecture. The luminous fraction of a structure that is mostly invisible, mostly cold, mostly silent. Dragonfly 44 is a window into that deeper layer. Not because it is dark. It is not entirely dark, not yet, but because it is dim enough, sparse enough, to show us what a halo looks like when the light almost did not come. It is a galaxy at the edge of visibility, a structure that exists in the space between the luminous universe and the dark one, carrying just enough starlight to be found, and just enough dark matter to remind us how much of the universe we are not finding. The missing satellites are not lost. They are simply there, in the way that a room is there even when no light has ever entered it, in the way that a structure can be real and complete and present without ever being seen. In Dragonfly 44, drifting quietly through the Coma cluster, its billion-old stars growing slowly dimmer, is perhaps the closest thing we have to a messenger from that invisible world, a structure that crossed the threshold just enough to tell us the threshold exists. And so we come to the stars themselves, the ones that are actually there, scattered thinly across that vast dark halo, each one burning with a quiet and ancient light. When astronomers studied the light coming from Dragonfly 44, not just how much of it, but what kind, they found something that told a story about time. The light was old. Not just old in the way that all starlight is old by the time it reaches us, having traveled across hundreds of millions of light years of space, but old in a deeper sense. The stars themselves were old. Their spectra, the particular colors and wavelengths woven into their light, carried the signature of stars that formed very early and then were left alone. This is something astronomers can read, the way you might read the age of a tree from the rings inside it. The chemical composition of a star's light, the balance of elements, the temperature encoded in its color, all of it speaks to when that star was born and how long it has been burning. And what the light of Dragonfly 44 says is this: whatever star formation happened here, happened early, and then, for reasons we can only partially reconstruct, it stopped. Perhaps the gas was stripped away by the tidal forces of neighboring galaxies pressing close in the dense Coma cluster. Perhaps the first generation of stars burned briefly and intensely and drove the remaining gas outward before it could collapse into new ones. Perhaps the halo itself, spinning too fast, never allowed the gas to settle and cool and fall inward the way it needed to. We do not know with certainty which of these is true, or whether all of them played some part, but the result is written in the light. A brief flowering early in the universe's history, and then silence. The stars that formed in that early window are still there, roughly 1 billion of them, by current estimates. But they are old stars now, red and cool and dim, burning through the last of their hydrogen with the unhurried patience of something that has been doing the same thing for a very long time. The universe itself is roughly 13.8 billion years old, and the stars of Dragonfly 44 may be nearly that ancient, formed perhaps 12 or 13 billion years ago, when the universe was still young and dense and full of gas that had not yet been used up. They have been burning quietly ever since. It is worth sitting with that number for a moment. 13 billion years. The Earth is about 4.5 billion years old. The Sun has been burning for roughly the same length of time, but these stars in Dragonfly 44 were already old when the solar system was forming. They were already in the second half of their lives when the first single-celled organisms appeared in Earth's oceans. They have watched, from their sparse and scattered positions within, that enormous dark halo, as the rest of the universe continued to evolve around them. New galaxies forming, new stars igniting, new planets condensing from cooling gas, while they themselves simply continued, slowly, fading. There is something very still about that image. 1 billion old stars spread across 60,000 light years of space, each one a little cooler and a little dimmer than it once was, drifting together through the dark, not because anything is holding them together in the way we usually think of galaxies being held together, but because the dark matter halo surrounding them, vast and invisible and patient, keeps them gently bound. They are, in a sense, passengers. Passengers inside a structure they did not build and cannot see, carried through the universe by a gravitational architecture that outweighs them by a factor of 1,000. And they are fading. Not quickly. Stars of this kind, old and red and low in mass, burn their fuel with extraordinary economy. They will not go out tomorrow, or in 1 million years, or in 1 billion. But the direction is set. Each one is spending what it has, slowly, and there is nothing coming to replace it. No new gas is falling into Dragonfly 44. No new star formation is stirring in its depths. The halo is there, as massive as ever, as dark as ever. But the light within it is not being renewed. Over the coming billions of years, the stars will exhaust themselves one by one. The most massive among them went long ago, in the early epochs when the galaxy was still young. What remains are the smallest and most frugal, the red dwarfs and the cooling remnants of stars that have already ended their active lives. White dwarfs, slowly radiating away the last of their heat into the surrounding dark. And as each one fades, Dragonfly 44 will grow a little darker. Not in any way that could be observed on a human timescale, or even on the timescale of civilizations. This is a dimming measured in billions of years, a process so slow it makes geological time feel hurried. But it is happening. It has been happening since the last star formed here, whenever that was, and it will continue until there is nothing left to see. Eventually, and this word carries more weight than usual here, because the timescale involved is longer than the current age of the universe many times over. Eventually, the last star will exhaust its fuel. It will not explode. Stars this small and old do not go out in fire. They simply cool. They radiate their remaining heat into the surrounding space, growing dimmer and dimmer, shifting from red to infrared to something that no instrument we currently possess could detect as light at all. And then it will be gone. And Dragonfly 44 will be what it always mostly was. A dark matter halo, drifting through the coma cluster, or whatever remains of it by then, carrying no light, emitting nothing, absorbing nothing, bending the space around it with the same quiet gravitational authority it has always had, but with nothing inside it that any telescope could find. The universe's most patient kind of quiet. There is no tragedy in this. Exactly. It is simply what matter does. over long enough time, it spins itself. It cools. It settles into the lowest available state and rests there. But there is something worth holding gently in the space before sleep. That right now, tonight, those stars are still burning. 13 billion years old, and still there, still sending their faint red light outward through the halo, outward through the coma cluster, outward across 320 million light years of expanding space. Still present. Still, just barely, visible. And somewhere, a small array of lenses built from parts that were never meant for this is patient enough and quiet enough to receive that light, to notice it, to say, something is here, something ancient, something almost dark. But not yet. Not yet.